This podcast was created as a supplemental learning resource for this course. The content is based on assigned course materials, including open educational resources, textbook chapters, instructor-developed explanations, examples, and applications connected to course topics. AI tools were used to help transform course material into a conversational podcast format, including the use of AI-generated narration. The AI narration is intended to make the material more engaging, accessible, and flexible for students. However, the podcast should not replace careful reading of assigned materials, reviewing course lectures, or completing course activities. Any interpretations, examples, or explanations included in the podcast are provided for educational purposes and are the responsibility of the instructor. Students should rely on the assigned readings, course lectures, and official course materials as the primary sources for exams, assignments, and class discussions.
Imagine you're running your latest data set through, whatever statistical software you like to use.
Right, like SPSS or R or whatever.
Yeah, exactly. And you check the summary output and everything looks, well, incredibly mundane. I mean, the mean of your X variable is 54.
Okay.
The mean of your Y variable is 48. The standard deviations are just, moderate. The correlation is essentially 0.
So it just looks like a totally normal, boring data set.
Exactly. The math tells you unequivocally that you are looking at a standard, maybe slightly messy, but completely unremarkable scatter plot.
Right.
But then you decide to actually plot the coordinates on a graph, and the data points form the exact unmistakable shape of a roaring Tyrannosaurus Rex.
Yes. The data source doesn't. It's such a classic example.
It really is. It's wild.
It's this beautifully terrifying reminder that the mathematics of summary statistics can and absolutely will deceive you if you, just allow them to operate in a vacuum.
Yeah, it's a huge trap.
Right. And the algorithm that generates that T-Rex scatter plot, along with, I think, 11 other wildly different shapes that share the exact same summary statistics, well, it's a modern wake-up call to data scientists everywhere.
And so today, that's exactly what we are dissecting on this deep dive. We're looking at why the math lies to us, right?
Exactly.
And how to avoid falling into those traps and really getting into the actual mechanical gears behind descriptive statistics.
Which is so important if you're a statistics student tuning in today.
Definitely. If you are one of those students, reviewing for midterms or just trying to solidify your foundational knowledge, consider this your masterclass.
Your masterclass on escaping number overload.
Yeah. We are going to decode exactly how we take a massive mountain of chaotic numbers and, force them to actually answer real questions.
And the necessity of this, it really goes back to how the human brain processes scale. I mean, it's just a biological limitation.
Wait, how do you mean?
Well, think about if you conduct a survey. Let's say you ask, 500 people to rate their current life satisfaction.
Okay, 500 people.
Yeah, and you put it on a continuous scale from -1,000 to +1,000.
That is a very intense scale for life satisfaction, but okay, I'm with you.
Right. But if you look at that raw data, you experience immediate cognitive failure. Your brain just gives up.
Oh, totally. Because you just end up staring at this towering spreadsheet.
Exactly.
Like one person submits a 550, the next person is at, -623.
Yeah, and then maybe 1135. Which actually violates the scale boundaries.
Oh, yeah. You always get one of those in a real survey. And then the next one is -1405.
Right. It's just a wall of text.
Yeah.
You cannot extract any macro-level meaning by reading 500 individual, highly specific numbers line by line.
You'd go crazy trying to find a trend in that.
You really would. And that paralysis, that is the whole genesis of descriptive statistics.
But that makes a lot of sense.
Yeah, before we even touch a single formula, we have to establish the philosophical grounding of what we are attempting to achieve here.
Right. And there's that quote from John W. Tukey that the source text mentions, which I think frames this perfectly.
Oh, I love that quote.
Yeah, he argued that it's far better to have an approximate answer to the right question, which is, often inherently vague,
Right.
than an exact answer to the wrong question, which can always be made mathematically precise.
Yes. That distinction right there between the exact and the approximate, that is the core tension in all of this.
It really is, because if you hand a stakeholder or a client that spreadsheet of 500 exact life satisfaction ratings, you are providing total, uncompromising precision.
You're giving them the literal truth of the data.
Exactly. No detail has been lost at all.
But you've answered the wrong question.
Right.
I mean, handing over the spreadsheet answers the question. What did every single individual person say?
Which is almost never what the client actually wants to know.
Never. It completely fails to answer the actual human question of, generally speaking, how satisfied is this population?
Yeah.
So, to answer the general, vague question, we actually have to intentionally destroy the perfect precision of the raw data.
That's such a wild way to think about it, destroying precision to find the truth.
We have to. We have to create an approximation. We basically have to compress the data.
Like an aggressive compression algorithm.
Exactly like that.
Because the complete, flawless description of the data is always the raw data itself. But because that's totally unusable for our brains, we have to find a way to step back.
And the very first step in that process, I mean, this is before calculating a mean, before looking for standard deviations. The first step is visual.
We have to escape the spreadsheet matrix.
Yes, turn the text into a geometry.
Because that visual first step is really the only way to guard against the T-Rex, right?
It is the only way. Because if staring at the raw numbers induces cognitive overload, we have to map those numbers into a visual space.
So our visual cortex can take over.
Exactly. Our visual cortex is highly optimized for pattern recognition.
So practically speaking, we take those 500 satisfaction scores and we just map them onto a simple coordinate plane.
Right, a basic scatter plot.
Yeah, we set up an x-axis, which is really just an arbitrary index, right? From 1 to 500 representing each respondent.
Just participant 1, participant 2, and so on.
And our y-axis is the actual satisfaction score running vertically. We plot the dots.
And suddenly, instead of a terrifying spreadsheet, we're looking at a cloud of dots.
Which is better, I guess.
It is an improvement. But, as you say, it still often resembles a swarm of bees.
Yeah, it's just a lot of dots.
You can identify the absolute boundary, sure. Perhaps you see dots reaching up to 800 and down to negative 900.
Right, the extremes are obvious.
And you might notice a denser clustering near the zero line, right in the middle. But trying to quantify that density visually, it's imprecise.
Because it doesn't aggregate anything. It just changes the format of the raw data from text to dots.
Exactly.
To actually summarize it, we have to stop looking at the individual dots and start forcing those numbers into groups.
Yes, we have to build a histogram.
The classic histogram.
The histogram represents our first truly deliberate act of data reduction.
Oh, okay. Unpack that.
Well, we are taking the continuous infinite possibilities of that y-axis, and we are slicing them into discrete, manageable chunks.
And we call these chunks bins, right?
Yes, bins.
Let's walk through the mechanics of that for the students listening.
Sure.
So we take our whole range of scores and we create a bin for, let's say, all the responses that fall between 0 and 200.
Right, that's our first bucket.
Then we just comb through the data set and count. If 85 people gave a score within that specific window, we draw a vertical bar over that bin that rises up to 85 on the frequency axis.
That's it. It's just a frequency count.
And then we repeat that process across the entire spectrum.
Yep, from negative 200 to 0, from 200 to 400, and so on.
And when we do that, the dots just vanish. They're replaced by a contiguous landscape of rectangular bars.
Which is brilliant, because this simple transformation reveals the macroscopic shape of the data.
You can instantly see the peaks, the valleys, the heavy tails, or, any sharp drop-offs.
Right. But the histogram introduces a massive subjective vulnerability into the analysis.
Okay, this is where it gets interesting.
Because when we build it, the software usually defaults to a certain bin width, right?
Yeah, SPSS or whatever just picks a number for you.
Exactly. But as the analyst, you have the power to change how wide those bins are. And that choice completely alters the narrative of the data.
It really does. It's one of the most consequential decisions. And honestly, one of the least discussed in basic data visualization.
I agree entirely. The bin width determines the resolution of your summary.
Let's use an analogy. Think about analyzing a local economy.
Okay.
If you are looking at the distribution of household incomes in a city, and you set your bin width to be, say, $100,000 wide.
That's a very wide bin.
Exactly. Yeah. Your very first bin captures everyone making between $0 and $100,000.
Right.
That single bar groups together college students working part-time, single parents struggling at the poverty line, and comfortable mid-career professionals.
They're all shoved into the same bar.
Right. The bin is so wide that it aggressively obscures the reality of economic inequality in that city.
You have over-smoothed the data.
Over-smoothed it, exactly.
You've destroyed so much detail that the resulting summary is actually misleading.
But then if you go the other direction, let's say you set your bins to be just $500 wide.
Oh boy.
Yeah, the histogram just shatters.
It does. You'll just have thousands of tiny jagged bars.
Right. You'll see a spike at $45,000, a massive drop at $45,500, and then another spike at $50,000.
Mostly just because people tend to round their salaries when reporting them on surveys.
Exactly. So now you're capturing every single piece of statistical noise and structural quirk in the data.
Right. You have undersmoothed it. You preserve the chaos, which defeats the purpose of the summary.
So finding the correct bin width is really a Goldilocks balancing act.
It is. You are constantly looking for the signal amidst the noise.
Which means, and this is kind of blowing my mind a little, there is no purely objective, mathematically perfect histogram.
No, there isn't.
Two highly ethical statisticians could look at the exact same data set, choose different reasonable bin widths, and present two visualizations that highlight entirely different trends.
This is a crucial realization for anyone studying statistics. The discipline is not merely a set of rigid algorithms that you just execute blindly.
It requires human judgment.
Absolutely.
Yeah.
Your choice of bin width is an interpretive act. You, the human, are deciding which variations in the data represent meaningful trends and which represent random fluctuations.
Okay, so once we have that visualization, once we have our carefully calibrated histogram, we need a standardized vocabulary to dissect what we are actually looking at.
We need to move from subjective visual interpretation to objective measurement.
Right, and that requires understanding the core trinity of descriptive statistics.
The big three: distribution, central tendency, and variance.
Those three pillars basically support the entire architecture of statistical analysis, don't they?
They do. Everything from your basic t-tests up to complex machine learning models relies on these foundational concepts.
Okay, let's tackle them systematically for the students. The first one is distribution.
Let's do it.
I think the easiest way to conceptualize distribution is to picture the classic game show Plinko on The Price is Right.
Oh, that is a fantastic analogy.
Right. You drop a disc down a massive pegboard, and as it falls, it bounces left and right off the pegs.
Driven entirely by gravity and random chance.
Exactly. Until it finally lands in one of the slots at the bottom.
The Plinko board is a brilliant mechanical representation of a statistical distribution.
So the pegs represent what, the random forces?
Yes, the pegs are the myriad random forces and variables acting upon a single data point in real life, and the slots at the bottom. Those are our histogram bins.
Okay, so over time, as you drop thousands of disks down that board, they start to pile up in the slots at the bottom.
Right, but they don't pile up evenly, do they?
No, not at all. Most of the disks tend to gravitate toward the center slots.
Because a path straight down is statistically much more probable than a path that bounces exclusively to the far left edge 50 times in a row.
So the resulting shape of those stacked disks, that visual mountain of chips that is the distribution?
Yes. In descriptive statistics, we use distribution primarily as a noun to describe that final empirical shape.
The shape itself is the distribution. It shows us exactly how our data points are spread out across the available possibilities.
But, and this is important, as you advance in your stats classes, you must also understand distribution as a generative mechanism.
What do you mean by generative?
Well, the layout of the pegs on that Plinko board, the underlying probabilities, dictates the final shape.
Oh, I see.
We actually spend a massive amount of time in inferential statistics working backward. We look at a pile of data, the shape at the bottom, and we ask, what specific arrangement of probabilistic pegs must exist in reality to have generated this specific shape?
That is fascinating. It's like reverse engineering the Plinko board.
Exactly.
But for our descriptive purposes today, we are just focused on summarizing the pile of disks we already have at the bottom.
Right, describing what's there.
Which brings us to the second pillar of the Trinity, central tendency.
Yes.
We are looking at this wide distribution of chips, and we are searching for the anchor. We're essentially asking, where is the center of gravity here?
We are attempting to identify the single value that best represents the entirety of the data set.
We're looking for the concept of typical.
But typical is a highly ambiguous term.
Yeah, it really is.
Which is exactly why we have distinct mathematical tools to approximate it. The mode, the median, and the mean.
Let's break those down. The mode is probably the most conceptually primitive of the three, right?
Definitely. It simply identifies the most frequently occurring value.
So you just scan the dataset, count the frequencies, and whichever number appears the most is crowned the mode.
Geometrically, it is the peak of the histogram. In a discrete dataset, it is literally the tallest bar.
But the mode is incredibly brittle, isn't it?
Oh, very brittle.
Like, if I have a data set containing the numbers 2, 2, 8, 9, 10, 11, 12, 13, 14, 15,
Okay, let me track that.
the number 2 appears twice. Every other number appears only once.
So mathematically, the mode is unequivocally 2.
Right. But if I summarize that data set for a client and claim that the typical value is 2, I am fundamentally misrepresenting the reality of the data.
You absolutely are. In that scenario, the mode is just a local anomaly that happened to repeat once.
It completely fails to capture the fact that the vast majority of the data points reside in the double digits.
And it falls apart even worse in continuous data.
How so?
Well, if we are measuring time down to the millisecond, the probability of any two data points being exactly identical drops to near zero.
Oh, right, because it's 1.004 seconds and the next is 1.007 seconds.
Exactly. Every number appears exactly once.
Yeah.
So a data set of 10,000 unique values technically has 10,000 modes, or no mode at all, depending on how you want to define it,
That's useless.
which forces us to group continuous data into bins just to find a modal class.
So the mode isn't great for this.
It has its uses, particularly with categorical data, where you just need to know the most common category, like what's the most frequent car color in a parking lot.
Oh, sure, white or black or whatever.
Right. But for robust numerical analysis, it is often inadequate.
So we abandon the mode and seek a more structurally sound anchor, and we move to the median.
Yes, the median. The median derives its strengths from position rather than frequency.
Okay, position.
To locate it, you must physically sort the data set from the absolute minimum value to the absolute maximum.
Just line them all up in order.
Line them up. And once the data is ordered, you identify the value sitting at the exact 50th percentile mark.
So literally the middle point.
Half the data is smaller than the median, and half the data is larger.
It is an order statistic. So if you have an odd number of data points, it's the literal middle number on the list.
And if you have an even number, you just locate the two central values and average them together.
Right. And the defining characteristic of the median, and the reason we love it, is its profound resistance to extreme perturbations.
It is mathematically insulated from outliers.
Let's test that insulation for the listener.
Okay, let's do it.
Imagine an ordered data set representing the daily revenue of a small coffee shop over 2 weeks.
How good.
The revenues are $400, $410, $420, $430, $440, $450, and $460.
Okay, so 7 days of data. The median there is the fourth number, which is $430.
Exactly. 3 days were lower, 3 days were higher.
A perfectly symmetrical, calm week of business.
Now imagine on the 8th day, a billionaire walks in, decides he absolutely loves the espresso, and tips the barista $100,000.
I wish I worked at that coffee shop.
Right. But now our new order data set is $410, $420, $434, $440, $450, $460, and $100,000.
An extreme outlier has just been introduced to the right tail of the distribution.
So if we recalculate the median, we have to find the middle of those 8 numbers.
Since it's an even amount of numbers now, 8, the middle falls between the fourth and fifth numbers.
Which are $430 and $440.
Right, so we average them, and the new median is $435.
Think about that. The introduction of a massive $100,000 anomaly barely moved the needle.
It shifted it by $5.
The median remained anchored to the dense cluster of typical daily revenues.
That's because the median cares only about rank order, not absolute magnitude.
Right, it doesn't care how big the biggest number is.
Exactly. The fact that the highest value is $460 or $100,000 is entirely irrelevant to the 50th percentile position.
That's wild.
This robustness is exactly what makes the median the gold standard when summarizing highly skewed data.
Like national wealth distributions, right? Or real estate prices in a city.
Yes, exactly.
Yeah.
Places where a few astronomical outliers like billionaires or mega mansions would otherwise totally distort the summary.
But sometimes you don't want to ignore the billionaire.
Very true.
Sometimes the total magnitude of the data actually matters. You want a summary statistic that is sensitive to every single drop of data in the pool.
And that requirement brings us to the most famous tool of all,
The mean.
the arithmetic mean, the classic average. It is ubiquitous, yet its actual physical properties are frequently misunderstood by students who just, memorize the formula.
Yeah, the formula is straightforward enough. We take the sum of all individual values.
Which is represented in formal notation by the capital Greek letter sigma, just so you aren't intimidated when you see it on a whiteboard.
Good tip. So we take that sum and we divide that total sum by n, which is the total number of observations.
That is the computation. But, as I always say, computation is not comprehension.
I like that. So how do we comprehend it?
We need to examine what the mathematical operation of division is actually executing upon the data.
Okay, well, division is basically an act of equalization.
Yes.
If I have a total sum of 15 and I divide by 3, I am taking that aggregate pool of 15 and slicing it into 3 perfectly equal shares of 5.
And applied to our data set, the mean is essentially a socialist equalizer.
A socialist equalizer, I love that.
If we return to our survey of 500 people rating their life satisfaction.
The one from the start of the show.
Exactly. We sum up all those scores, the negative thousands, the positive hundreds, into one massive global aggregation of satisfaction.
We pool all the emotion together into a giant vat.
We pool it, and then the division by n redistributes it.
So the mean calculates exactly how much satisfaction each of those 500 people would possess if we mandated that every single person must have the exact same amount.
It takes the excess from the extreme positive outliers, the really happy people, and uses it to fill the deficits of the extreme negative outliers.
Until the entire population is perfectly level.
The mathematical consequence of this equalization is profound.
How so?
The mean is the only distinct value that can be substituted for every single data point in your data set while preserving the exact original sum.
Oh, wow.
Right. It is a perfect surrogate for the total aggregate magnitude.
That's a great way to look at it. But there's another way to conceptualize the mean, and I think this physical analogy from the sources is really critical for understanding the math that comes later.
Yes, the center of mass.
Right. The mean is the precise center of mass of the data.
If you visualize the x-axis, not merely as a line on a page, but as a physical wooden plank resting on a fulcrum.
Like a seesaw on a playground.
Exactly, a seesaw. And you place a 1-pound weight at the location of every data point.
Okay, let's walk through that. So if I have data points at the numbers 2, 4, and 9.
You put physical weights at the 2-inch mark, the 4-inch mark, and the 9-inch mark on this ruler.
Okay.
The mean is the exact mathematical coordinate, where you must place the fulcrum underneath that ruler so that it balances perfectly horizontally with 0 tilt.
Let's calculate that to prove it. The sum of 2, 4, and 9 is 15.
Divided by 3 weights, so the mean is 5.
So I place the fulcrum at the 5-inch mark.
And it balances perfectly.
Because the torque exerted by the weights on the left side of the fulcrum is perfectly counteracted by the torque exerted by the weights on the right.
Exactly. The center of mass property is brilliant.
It really makes it visual.
But, and this is where students often stumble, it is also the very thing that traps us when we move to the final pillar of our trinity, variance.
Because the central tendency, the mean or the median, only tells us where the seesaw balances.
Right. It provides 0 information about how the weights are actually distributed along the plank.
I mean, a data set of 5, 5, 5 has a mean of 5.
Sure.
But a data set of negative 1005 and positive 1010 also has a mean of 5.
The centers are identical, but the architectures of the data are wildly different.
One is completely clustered together and the other is spread out to the extremes.
Right. We have summarized the sameness. Now we must summarize the differentness.
We need a metric that quantifies how much the data points diverge from each other.
And the most rudimentary approach to this is just calculating the range.
The distance between the absolute minimum and the absolute
A
maximum.
maximum minus minimum. Simple.
It is a vital first check, honestly. Like, if your survey software limits responses to a 1 to 7 scale and your descriptive output shows a range of 94,
You immediately know there is a catastrophic data entry error.
someone typed a typo.
Yes. The range is a highly sensitive tripwire for anomalies. But as an actual descriptive summary of variance, it's inherently flawed.
Because it ignores like 99% of the data.
Exactly. It calculates the distance between the two most extreme outposts and assumes absolutely nothing about the landscape in between.
That's not good enough. We need a metric that incorporates every single data point. We need to know how much all the numbers differ from each other simultaneously.
To do that rigorously, without relying on a central anchor, you would technically have to calculate a different score between every possible pair of numbers in the dataset.
Every possible pair. Let's scale that up and see what it looks like.
Okay.
If I have a tiny data set of just 10 items, and I want to compare every item to every other item to find the average difference, well, the formula for unique pairings is n times n minus 1 divided by 2.
So 10 times 9 is 90, divided by 2 is 45.
I have 45 unique different scores to calculate and average. That's tedious but doable by hand.
Now scale it to our dataset of 500 survey respondents.
Oh boy. 500 times 499 divided by 2. That is 124,750 unique different scores.
Yeah. We are immediately back to the initial problem of information overload.
We cannot intuitively process 124,000 different scores.
The pairwise comparison matrix scales quadratically. It just becomes computationally and cognitively unmanageable very quickly.
So we need a shortcut.
We do.
Instead of comparing every data point to every other data point, what if we use the anchor we just built? What if we compare every data point to the mean?
That is the pivotal conceptual leap in statistics. The mean acts as a central proxy.
So instead of 124,000 pairwise comparisons, we only have to make 500 comparisons.
Exactly. We just measure the distance of each individual data point from the central hub.
We calculate the deviation score.
Deviation scores.
We take a data point, let's call it x, and we subtract the mean, x minus mean.
So if the mean is 5 and the data point is 8.
The deviation is positive 3. The point is 3 units above the mean.
Right. And if the data point is 2, the deviation is negative 3. It sits 3 units below the mean.
You generate 500 of these deviation scores. Some are positive, indicating they sit on the right side of the fulcrum.
And some are negative, indicating they sit on the left.
And now, logically, we want to find the average of these deviations. We want to know the typical spread.
Right, that's the goal.
So we take all 500 deviation scores, add them all up to find the total sum of the differences, and divide by 500.
And this is where the mathematics violently revolts against human intuition.
Yeah, this is the trap.
If you execute that logical series of steps, if you sum the raw deviation scores, you hit a mathematically inescapable brick wall. The sum will be 0.
Every single time.
Every single time, regardless of the data. The sum of the raw deviations from the mean is always precisely 0.
This is the zero trap.
Yeah.
And it traces directly back to the physical property of the mean we established earlier. The mean is the center of mass. It is the exact balancing point of the seesaw.
And for a seesaw to balance, the total downward force on the left side must perfectly equal the total downward force on the right side.
Which means the sum of all the negative deviations, the distance of the weights on the left, must perfectly match the sum of all the positive deviations on the right.
So if the left side deviations sum to, let's say, negative 427, the right side deviations mathematically must sum to positive 427.
And negative 427 plus positive 427 equals 0. The deviations systematically annihilate each other.
They wipe each other out. So if you calculate the average of the raw differences, you are essentially dividing 0 by n.
You just get 0.
You mathematically prove that the average difference in a wildly varying data set is nothing.
Which makes no sense. The math has completely failed to describe reality because the negative signs basically acted as a self-destruct mechanism.
Exactly. So we're stuck.
The physical reality of the data clearly shows variance, but our algebraic summary collapses to 0.
To proceed, we must invent a mathematical workaround. We have to eliminate the negative signs before we run the summation.
The most obvious intuitive workaround is to simply strip the negative signs away. We just use absolute value.
Right. If a deviation is negative 3, you ignore the sign and treat it as a positive 3.
You treat every deviation as a simple positive distance. You sum up all those positive absolute values, and you divide by n.
And that computation yields a perfectly valid, highly intuitive metric known as the mean absolute deviation, or MDA.
MAD. It tells you exactly what you want to know. The average absolute distance of a data point from the mean.
It is elegant. It completely bypasses the 0 trap without breaking a sweat.
So why is MA largely absent from introductory statistics? Why do we force students into the much more complicated gymnastics of variance and standard deviation?
It's a great question. The issue is that MAD is mathematically intuitive, but it is algebraically brittle.
Brittle how?
Well, the absolute value function creates a sharp V-shaped corner at 0 on a graph.
Okay, I can picture that.
In calculus, that sharp corner is non-differentiable. You cannot easily calculate a slope at that exact point.
Which means if you try to use MAD later on in complex optimization algorithms like training a neural network or running a sophisticated regression model, the math literally chokes at 0.
Yes. Furthermore, MAD treats all deviations linearly.
What does that mean in practice?
It means a deviation of 10 is penalized exactly twice as much as a deviation of 5.
Which sounds fair, right?
It sounds fair, but in many statistical paradigms, we actually want to disproportionately penalize extreme outliers.
Oh, I see.
We want a deviation of 10 to hurt the model much more than twice as much as a deviation of 5, because extreme errors are often exponentially more problematic.
So to achieve that nonlinear penalty and to create a smooth, differentiable curve that calculus can handle, statisticians abandon the absolute value and embraced a totally different tool to destroy the negative signs.
Squaring.
We take every single deviation score and we multiply it by itself.
Right.
Let's walk through that. If the deviation is -3, we square it. -3 times -3 becomes a +9.
Because a negative times a negative is a positive. The negative sign is obliterated.
And if the deviation is +4, it squares to 16.
Right. Squaring solves the zero trap entirely. Every deviation, whether it was originally above or below the mean, is transformed into a positive magnitude.
When it solves the outlier penalty you mentioned,
Exactly.
because a deviation of 2 squares to 4, but a deviation of 10 squares to 100.
The outlier is heavily penalized in the resulting math.
So we perform this squaring operation on every single data point in our set. We then sum all of those positive squared values together.
And that massive aggregate number is a term that haunts statistics students everywhere.
The sum of squares, or SS.
The sum of square deviations. It is the foundational building block of all inferential statistics.
ANOVAs, regressions, they all run on the engine of the sum of squares.
They absolutely do.
But the sum of squares is an aggregate. It's a total pool of squared variance.
Right.
It grows larger simply by adding more data points. So to find the average squared variance, we must divide that aggregate pool by n.
We take the sum of squares and we divide it by the number of observations.
And the result of that division is the variance.
We have successfully bypassed the zero trap, incorporated every single data point, penalized the outliers, and calculated an average metric of spread.
We did it.
We did. But there's always a but in statistics, in solving the algebraic problem of the negative signs, we have created a severe geometric problem.
Because the units are completely broken now.
Entirely broken.
That
Think about what we just did.
Okay.
Let's say our original data was measuring the height of oak trees in meters.
Okay, meters.
The deviations from the mean were in meters. But when we squared those deviations to get rid of the negative signs, we mathematically transformed meters into squared meters.
Oh, we turned linear distance into two-dimensional area.
Exactly. So when we calculate the variance, the final number is expressed in squared meters.
So if you tell a botanist that the variance of their oak trees is 14.5 square meters.
It is conceptually meaningless as a descriptive summary of height. You cannot visualize a squared meter of height.
You literally inflated the data into a higher mathematical dimension just to dodge the zero trap.
Yes. And to make the summary usable again, we have to deflate it. We have to bring it back down to the first dimension.
We must reverse the squaring process.
And how do we do that?
We take the square root of the variance.
And that final corrective operation yields the absolute holy grail of descriptive statistics, the standard deviation.
The square root of the average square deviation from the mean.
By taking the square root, we collapse the units back down from squared meters to linear meters.
So the standard deviation is expressed in the exact same units as the original raw data.
It finally provides the intuitive answer we've been searching for since we first looked at that messy spreadsheet.
Which is, on average, how far does a typical data point stray from the center?
Yes. If the mean tree height is 20 meters and the standard deviation is 3 meters, you instantly have a functional mental model of the forest.
You know the anchor and you know the typical spread around that anchor.
It is a phenomenal journey of mathematical engineering.
It really is when you trace the steps. We encountered a physical reality, the center of mass, causing deviations to sum to zero.
Right.
We engineered a theoretical workaround by elevating the math into squared dimensions. We calculated our averages in that abstract space, and then we used a square root to pull the final answer back into reality.
And recognizing that it is an engineered solution is vital.
It's not magic.
No, the standard deviation is not some natural law of the universe. It is a human invention designed to solve a specific structural problem in the math.
In fact, the textbook notes that in principle, to get rid of the negative signs, you could raise the deviations to any even-numbered power.
Oh, absolutely.
You could raise them to the power of 4 or 6 or 8.
An infinite number of even dimensions. And mathematically, those higher power deviations exist.
Wait, really?
Yes. They define higher order moments of a distribution, like kurtosis.
Kurtosis.
That measures the thickness of the tails of the distribution. But we standardized on the power of 2 for variance because it bridges perfectly with the Pythagorean theorem in Euclidean geometry.
Ah, keeping it elegant.
It makes the subsequent mathematics of multidimensional space incredibly elegant, yes.
Okay, so we have built our definitive tools now. We have visualizations. We have the mean to locate the exact center of balance. We have the standard deviation to precisely quantify the spread around that balance. We have successfully compressed the massive, chaotic 2-hour movie of our raw data into a crisp, highly informative 2-minute mathematical preview.
We have. And if you are a student, this is the point where you might feel confident simply running your data through a script, looking at the mean and standard deviation, and drawing sweeping conclusions.
Which brings us right back to the plot twist from the beginning.
Yes, the danger of trusting the preview over the movie.
We opened with the modern data source dozen, but the foundational cautionary tale of relying blindly on summary statistics actually dates back to 1973.
Yes, with a statistician named Francis Anscombe.
Anscombe's quartet.
Right. In the early 1970s, the field of statistics was undergoing a massive paradigm shift. Computations that used to take weeks by hand could suddenly be executed in seconds by mainframes.
That must have felt like magic.
It did. But it created a growing, dangerous hubris. People started believing that computer-generated summary statistics were the ultimate truth, and that plotting data visually was just an archaic, unnecessary step.
Like, why draw a graph when the computer just gives you the exact answer?
Exactly. Anscombe wanted to shatter that hubris. So he engineered 4 distinct data sets.
4 pairs of X and Y coordinates.
He designed them so that if you ran the standard descriptive statistics through a computer, the output for all 4 data sets was mathematically indistinguishable.
Identical.
Completely. The mean of X was precisely 9.0 across all 4. The variance of X was 11.0.
Okay.
The mean of Y was 7.50. The variance of Y was 4.12. And the Pearson correlation coefficient was 0.816.
So if you look solely at the summary matrix, these 4 data sets are identical twins.
Quads, actually.
Right, identical quads. They have the same center of mass, the same standard deviation, the same linear relationship. The math screams that they are the exact same phenomenon.
But Anscombe's trap is sprung when you actually plot the coordinates on a Cartesian plane.
I am looking at the visualizations in the source material right now, and the divergence is just staggering.
Walk us through them.
Okay, dataset 1 is a classic, somewhat messy scatter plot. The dots trend upwards in a noisy, organic-looking cloud. It is a textbook linear relationship.
Right. That is the baseline. It behaves exactly as the summary statistics suggest it should.
But dataset 2 is entirely different. It is not a messy cloud at all. It is a perfect, smooth, mathematical parabola.
An inverted U-shape.
Exactly. There is absolutely no linear relationship here, yet the correlation statistic claimed there was.
Because the linear math forcefully mapped a straight line over a pronounced curve, completely missing the true structural reality of the data.
Dataset 3 is a flawlessly straight, ascending line of dots. It is a perfect linear relationship, except for one single, massive outlier located far above the line.
And that single extreme value exerted so much gravitational pull on the mean and the variance that it warped the summary statistics of the perfect line to match the messy cloud of dataset 1.
The outlier literally hijacked the mathematical summary.
It did.
And dataset 4 is perhaps the strangest of them all. It isn't a spread of points at all. It is a single vertical column of dots stacked directly on top of each other at the x equals 8 mark.
Right.
And then way off to the right at x equals 19, there is one solitary dot.
And that single point of extreme leverage acts as a pivot. It forces the statistical algorithm to draw an angled trend line through a data set that is fundamentally just a vertical stack.
Anscombe proved mathematically what the data source doesn't prove visually with the T-Rex.
Yes.
Descriptive statistics are blind. They are highly efficient compression algorithms, but they lack spatial awareness.
They will dutifully calculate the center of mass and the spread of a parabola, a straight line, and a dinosaur, and return the exact same numbers.
Which is terrifying.
This is the paramount lesson of descriptive statistics. The tools are incredibly powerful, but they must be supervised by human visual intuition.
You can't just set it and forget it.
Never. If you calculate the mean and standard deviation without first looking at the histogram or the scatter plot, you are essentially flying a plane in a thunderstorm, using only instruments you haven't even calibrated.
You have to map the territory before you can trust the coordinates.
Precisely. You must look at the shape of the data. You must verify that the distribution is unimodal and relatively symmetric before you trust the mean to represent the typical value.
What happens if it's not?
Well, if the histogram reveals a massive bimodal split like 2 distinct peaks, the mean will fall right in the empty valley between them.
Meaning the mean represents absolutely nobody in the data set.
Exactly. Think about a medical trial. If a drug works perfectly for half the patients, but catastrophically fails for the other half, a bimodal distribution emerges.
2 humps on the graph.
Right. The mean might sit right in the middle, suggesting the drug has a, mildly positive effect overall.
But nobody actually had a mildly positive effect. They either got cured or they crashed.
Exactly. Relying on the math without looking at the shape of the distribution could have devastating real-world consequences in that scenario.
Wow. We have covered immense ground today.
We really have.
For the statistics students reviewing this, let's just trace the arc of the architecture we've built.
Good idea. We began with the cognitive impossibility of raw data, that towering spreadsheet of numbers that paralyzes analysis.
We learned to escape that matrix by deploying visualizations, translating continuous data into the discrete, grouped bars of a histogram.
And we recognize the subjective power of the analyst in choosing bin widths that clarify rather than obscure.
Then we established the core trinity: distribution to define the shape, central tendency to anchor the data, and variance to quantify the spread.
Right. We navigated the fragile nature of the mode and the robust, order-based insulation of the median.
We broke down the mean, not just as a formula, but as a socialist equalizer and the physical center of mass balancing on a fulcrum.
We confronted the zero trap, recognizing that the balancing property of the mean mathematically forces raw deviations to annihilate each other.
And we performed the mathematical gymnastics required to survive that trap. We abandoned the absolute value of MAD for the differentiable power of squaring.
We calculated the sum of squares, divided it by n, to find the variance in an abstract squared dimension.
And then deployed the square root to drag the standard deviation back into linear reality.
And finally, we looked at Anscombe's quartet and the data source dozen, cementing the absolute necessity of visual verification against the blindness of summary algorithms.
It is a brilliant, interconnected system of engineered solutions, and the fact that it is engineered is what I find most compelling here.
How so?
Well, we use the standard deviation constantly, but it was just a creative solution to a specific algebraic roadblock.
It was.
We chose to square the deviations, but we could have raised them to the power of 4 or 6 or 8, exploring infinite dimensions of variance.
The tools of statistics are not finished. They are continuously evolving. The methods we discussed today were codified over a century ago to summarize data that could literally be written in a ledger.
And today,
Today, we are dealing with hyperdimensional data, massive matrices of billions of parameters in neural networks. The foundational logic of central tendency and spread remains, but the compression algorithms must become exponentially more sophisticated.
which means the textbook isn't closed. The tools you are studying right now were invented by people trying to make sense of the chaos in front of them.
Exactly.
The next time you are staring at a massive, incomprehensible data set, and the existing tools aren't capturing the reality of the shapes you see, what entirely new mathematical dimension are you going to invent to describe it?
The future of data science belongs to those who understand the mechanics of the old tools well enough to forge the new ones.
Keep plotting the dots. Keep looking for the dinosaurs hiding in the math. We'll see you on the next deep dive.